Today we're going to talk about principal component analysis. This is pretty much the starting point, the building block of multivariate data analysis. It's a very important concept to kind of grasp as you move forward with your multivariate data analysis. So I'm just going to give a bit of an introduction into multivariate data analysis in general and why we do that. And then we're going to get into principal component analysis proper, and I have two examples that I will show you live using the unscrambler as well. So in general, our world is multivariate. There's very few things in this life that are univariate. So we have lots of problems, say the weather, that has lots of different factors that working together makes it up, such as, in this case, wind, air pressure, temperature, your dew point, your season. If you only look at the temperature, it doesn't tell you whether you need a raincoat that day, for example. So you need to understand all of these major factors all at once to really understand what's going on with the weather. And there's lots of different types of sensors to do that. And they all have different scalings and different ways that they react with each other. And this is where we need our multivariate mathematics and chemometrics to kind of bring all of those differing data together into a picture that we can truly understand. If you've ever worked in any sort of manufacturing process, you may have seen something like this. These are control charts. And in this case, we're looking at our data and it looks like everything's perfectly under control. For our temperature, we have our target. That's going to be the center dashed line. And both of them, and their top and bottom dashed lines are limits. So as long as our measurements stay within this space, then we think that everything is behaving properly. But what happens when these two measurements are actually correlated with each other? So now we're looking at our temperature plotted against our pH, or vice versa. And we can see in our multivariate view, if we extend our univariate limits, then everything still looks like it's under control. However, we can see there is this one data point that when we look at our multivariate view, it's very clearly different from the rest of our data. There is this nice pattern that we see in our multivariate view of a correlation between temperature and pH, and this particular one doesn't follow that particular pattern. We can develop a multivariate method and put in new limits that correspond to that multivariate space. And then we can trigger a warning to say that, hey, this particular data point is actually out of spec, even though we wouldn't have seen it if we were only looking at the individual variables themselves. Another reason that we might use multivariate data analysis is if there's a need for an indirect observation. For example, what's the temperature of a furnace? There aren't really any direct measurements possible with a thermometer, for example, because they would melt. That is the whole purpose of the furnace, right? So how do we measure what the temperature actually is? Well, what we know from our first principles is that IR emission is related to the temperature of a source. So we can use an IR emission spectrometer to determine what the temperature of that furnace is. And these types of indirect measurements often need a multivariate analysis approach. We also, in multivariate data analysis, these are considered soft or empirical modelings. So instead of staking from your first principles and working your way up to a solution, we're observing a process. We're observing our world and making assumptions about that and trying to model what's going on based on our observations. Okay? And these are our multivariate methods are required to analyze the data in order to understand these things. And we do make use of our background knowledge and our theory in order to have the correct interpretation of what we're seeing, and also for the most comprehensive validations. So in practice, data analysis is going to be about 70% of it is going to be application knowledge and your common sense. These are the things that you bring to the analysis that are very subject matter expertise information. The remaining 30% is your statistics and your mathematics. And this is where the unscrambler comes into case, and it helps you with the math and statistics so you don't have to worry about that so much as applying your application knowledge and your common sense to the output. We don't want you to have to worry about the math. Math and the statistics is straightforward. It's the interpretation and the analysis of the outputs that really matter. Now, one thing, anytime you're doing statistics, the thing that we must put as a caveat is you have to be careful about causality versus correlation. You have to be very careful when you're interpreting your data. There's a famous survey in Danish rural towns that showed a correlation of 0.75 between the number of babies born and the number of storks found in the area. We all know that the interpretation of that data would not be that the number of storks are bringing your babies to the area. So just be very careful that even though there's a correlation, it does not mean that one is causing the other. So one thing we want to do is pull out our hidden data structures. We start with our full information. These are our observations, and that can be broken down into your data structure and your noise. And what's considered your data structure and what's considered your noise can be very dependent on your particular application. For example, if we have a matrix of A, B, and C, and if what we're really interested in measuring is the amount of B, then the curves here that are due to A and C are going to be part of your noise, and the B is going to be part of your data structure. If, however, what we care about is C, then now C is our data structure that we care about, and A and B is going to be our noise. So you need to be very careful before you go into your data analysis that you know what you're looking for. It can be a very high-level thing. Say, I want to see, what if there's more than one thing that's going on here. But just be aware that what you consider data and what you consider noise can be very dependent on your particular analysis. There are different types of methods that you can choose from. We can do some exploratory data structuring. This is unsupervised looking at your data. This is kind of your first pass, trying to understand what your data is. Then we can get into discrimination and classification. You can separate things out into different groups of data. You can do some quantitative analysis from this, and there's some examples of how we would do that. And then there's regression and prediction. So that's taking a set of variables, seeing how they're related to something else. And this is going to be our indirect observations. Again, this webinar, we're going to focus mainly on this explorative data structure and modeling. This is going to be unsupervised, looking for patterns, and qualitative analysis. And this is going to be principal components analysis. So some of the uses for principal component analysis, as I've mentioned already, is exploratory data analysis. When you're first taking a look, I don't even know what I'm looking at right now. Do things correlate? Are they important at all? This is where we start. We also want to extract information. So for spectroscopic data, for example, these extract information and noise removal go very hand in hand. You want to reduce that noise, pull the information out that's important to you, as well as dimensionality reduction. I'm going to use the example of spectroscopy again. You've got hundreds of wavelengths that you're looking at, and that's very difficult to visualize and wrap your brain around this multi-hundred dimensional space. But in principal components analysis, we often can bring that down to, say, 2 or 3 dimensions, and it makes it a lot more easy to interpret. So this is a view of our overall structure. We have our X block of data. That is the information that you're putting into the analysis. And from that, you're going to build your model, and there'll be some sort of error left over. The model is basically an approximation of your original data set. It's pulling out the most important information and ignoring the remainder bits. So we need to talk a little bit about your principles of projection. So each variable will define an axis. So variable 1 is going to be x1, variable 2 is its own direction, and variable 3 is another direction. In the unscrambler, every row is an object or a sample if you're used to that terminology. And for each object, you're going to have a value for each one of your variables. And you can plot that as a point in this three-dimensional space. All right, and now we do that for all of the points, and we see that they fall into this space here. And the whole data table makes a swarm of points in this original variable space. What we really care about is what is the structure of this entire swarm. So what we do is we mathematically determine which direction is showing the most amount of variability in our data, regardless of what the original variables are. And what we can see is we define this particular vector as principal component 1. Okay, this points in the direction of the maximum variation by definition. And then we look straight down that line and try to find the next direction that has the next most amount of variation. So we've got this PC1, we're taking our eye, we're looking straight down that line. So this black dot in the center here is the principal component 1 vector. And then we define which direction principal component 2 is based on how close they are to this line. And you can continue that until all of your data has been explained. Okay, once we have two principal components, we have this plane that is describing our data, or a window that describes this data the best. And we can project these points into that new window of space. Now, the maximum number of PCs that you can calculate is going to be the minimum of either the number of variables you start with or the number of samples minus 1. Keep in mind, it is very rare that you get to this maximum number of PCs. When I'm doing my analyses, depending on the type of data I'm looking with, if I get to more than about 4 or 5 PCs, I start getting nervous and thinking that I'm over modeling, which we'll talk about in the a little bit later in the webinar. Except for, say, environmental or biological samples, those can sometimes get into the range of 15 or 20 principal components before you can truly understand it. It makes it a little bit harder to visualize, but you can break it down and interpret each component individually. So one of the things is, once we've created our new space in principal component space, is we want to have a scores plot. And the scores is what tells us where the individual sample falls along this new vector. Okay, so if we have the center, the mean of our swarm of data is going to be defined at the center of this principal component. And then it's going to be the distance from that mean is going to be the score for each individual data point. Now, depending on which direction you define as positive, something in this case, we're going to say that our vector is going from left to right. So anything that is to the right of this mean data point is going to have a positive score, and anything to the left of this mean is going to have a negative score. So that's all fine and dandy that we know what the scores are in PC1, but what is PC1? What does that mean? So we need to understand what direction that vector is going in by correlating that back to the original variables. So the loading for the individual variables is going to reflect the relative weight given that variable. So how close to that original vector direction is this new principal component direction going? Okay, and your loading is going to be a scaled relationship to the cosine of the angle between the vector of the principal component and the original variable vector. One thing we do when we start with principal component analysis is we mean center the data. This happens automatically in the unscrambler unless you actively uncheck that. And the reason why we do this is because if you're looking at the data, remember I said that the principal component 1 is by definition the direction of the most variation. Well, by definition, if you do not mean center, the first principal component will be from the origin to the center of this data swarm. So we just go ahead and subtract the mean from all the variables so that our data swarm is around the origin. So that prevents that from being an issue. One thing we may need to do is if we're working with disparate types of data streams, say for example the pH and temperature, things like that that are on very different scales, one thing we may need to do is standardize them. So if this is our raw data, this is looking at a box plot at the top, which shows our quartiles. So the bottom of this whisker is going to be the mean, or the minimum, my apologies, and the top is the maximum. And this box in the center is going to be from the 25 to the 75 quartile, and the center line is going to be your median value. As we can see here, variable 3 has a much larger nominal value and a much wider variation range than either 1 or 2. And what this means is if we put this directly into our data analysis, our principal component analysis will tell us that variable 3 is going to be the most important solely because the numbers are large. So what we do is, again, we can scale, we can mean center so that they're all around 0. But as you can see, we still have a lot of disparate variations. So we're going to say that, variable 3 is varying a whole lot more than 2 or 1, especially 1. You can almost barely see the variation in 1. So then we divide by the standard deviation, and that puts each individual variable kind of on an even playing field so that they start off with the same amount of weight based on their values. And when you run your analysis, you can tell that if now they start on the same playing field, if one of them really stands out, then it's much more clear and easier to interpret that that truly is an important variable for your analysis. So I'm going to show our first data example. And let me make sure I get my right version of the unscrambler open. And I'm just going to open this data file. So what I have here is some data on McDonald's food. And so it's measuring different components of our food, the kilocalories. Here we've got our protein concentration, our carbohydrates, our fat percentages, and saturated fat. One thing I have done is I inserted a category variable so that we can have a drop down to give these different categories so we can identify them more easily when we do our analysis. One of the first things I want to do is under tasks, I'm going to analyze descriptive statistics on just my nutrition data. Now this gives me my box plots, so I can take a quick look at how these variables relate to each other. They're not hugely different from each other like we saw in the slides, but they are definitely on very different scales, and some of them have different variations to them as well. So this is an indication that I'll probably need to mean center and scale my data before applying my analysis. So I'm going to go back to my data matrix, and under Tasks, Analyze, I'm going to choose Principal Component Analysis. And you'll get this nice wizard for running your analysis. So the first thing I'm going to do is change this. I just want to look at my nutrition data. You see that it's giving me my maximum components that I can calculate is 5. That is based on the fact that I only have 5 variables that I'm putting into my data. And I said I wanted to weight my data. So I'm going to go into this weight file, and I'm going to select the individual variables that I want to weight. You can do them manually if you want, or I can select all. And I'm going to select this one. This is my subtract the mean, divide by standard deviation. And I'm going to click Update. And you will see that the weights here have been updated. If you do not see them change here, they have not been applied weights. That's kind of a common issue that people run into from time to time. Everything we do in the unscrambler has some sort of validation to it. And we tend to do cross-validations. It's sort of our first step. So I'm going to go into Setup here. And this is a full cross-validation. I only have 13 samples. It makes sense to pull out individual samples. If you have more than, say, 30 samples, you would probably switch to a random cross-validation. If you stay at the leave one out when you have lots of data, it gives you an overly optimistic view of your model. So OK and OK. Now this is your general view of what your data is when you run a principal components analysis. And we'll see at the top here, we've got our scores and our loadings. These are those first two things that we've talked about. I'm going to go ahead and put labels on here. There's a little checkbox at the top, show labels, and I'm going to label my loadings as well. Now in my loadings, what I like to do is put on my correlation loadings. This puts these on a unit circle. It helps me identify a little bit more clearly what variables are the most important. Things that are inside the center ellipse are explaining less than 50% of that direction of that principal component, and so are probably not that important. Things that are in the between the two ellipses explain anywhere from 50 to 100% of that particular one. So the way we interpret this, we interpret our scores and our loadings side by side. We can see that principal component 1 is plotted on the x-axis. Okay, so principal component 1 is mostly due to our energy, our kilojoules, and our fat content. Okay, there's a little bit of protein in there as well, but mostly the energy and the fat. And then principal component 2 is going to be read from the y-axis, is mostly the carbohydrates and a little bit of protein as well. Now, the cool thing is we look at these side by side. These correlate directly. Things that are in your scores plot on the right-hand side mean that they are going to have high values of your energy and fat percent and protein. Things that are on the left-hand side of the center line are going to have lower values of those same variables. Things that are high at the top of your y-axis here are going to be high in carbohydrates and lower in protein. Things that are at the bottom are going to be higher in protein and lower in carbohydrates. So let's take a look at what's over here. Things that are in this bottom right-hand corner are your burgers mostly, and those are you're going to be the ones with your higher protein content because they contain meat. So you can see how these interact with each other. One thing that we can do in the unscrambler, which is very handy, you remember I put those category variables in there. If I right click and do sample grouping, I can define some samples based on those categories. I'm going to pull those over, and I'm actually going to leave the label as the name instead of the group. We're going to say OK and give my legend. So what we can see here is that all of our burgers kind of hang out together. All of our ice creams hang out together here. And then our French fries and our apple pie kind of sit next to each other, which you might think is a little strange until you think about McDonald's apple pies are actually fried. So it makes sense that they would have similar nutritional values to something that was fried, like the French fries. So that's our first example. So we talked about this a little bit already, but how exactly do we interpret our models? So the first thing you want to do is take into account the number of components that you want to look at. And I'll break this down a little bit more in the later slides. Then we're going to look at our scores. You want to make sure that your scores are evenly distributed. Look for any patterns. Are there any groupings or similarities? And that's what we just did. We noticed that all of our burgers and sandwiches were grouped together. Our ice creams were grouped together. And then you can use your loadings to understand those correlations. Why are the burgers grouping together? Why is the apple pie and the French fries grouping together? And we can see that was due to the carbohydrate contents. Okay, and the fourth one here is you can look at your biplot. This is an overlay of your scores and loadings on top of each other. It's not a personal preference of mine to use that. I prefer to look at them side by side because they are on different scales from each other. So for me, it makes it a little bit more difficult to interpret, but for some people, it helps them interpret a little bit better. So that's sort of a personal preference, whether you prefer to look at your scores and loadings side by side or look at your biplot on top of each other. So how do we choose the number of components we want to use? So we look at our explained variance. That was in the lower right-hand graph in our example, and I'll show that in our next example a little bit more clearly. And what we want to do is you follow your calibration variance and you follow your validation variance. And what you do is look for that first local minimum. If you're looking at the residual variance, where does it start to plateau off at the bottom? If you go too far, you get to a case of diminishing returns. Adding an extra principal component explains a very small amount of your data. And I'm going to show again real quick my unscrambler. You can see here on your loadings, it tells you principal component 1 here explains 42% of your information. Principal component 2 explains 34%. We can increase these, change that. Principal component 3 is going to be 18%, and so on. I find that when it starts to get down to single digits, that tends to be a good rule of thumb of that you don't need to use that principal component unless you can really justify that you want to use that one. So we look at our validation variance as well, and when we see this red line starting to diverge away from the blue line, we need to stop. That's telling us that we're losing our predictability. By definition, your calibration variance will trend towards 0. The validation variance gives you a good guess of what's going to happen when you throw new data in. And when that starts to diverge away, you're saying, I'm putting new data in, but I'm not able to predict it well anymore. So as soon as that starts to move away, take one less principal component than that. Your components should be interpretable. That's important. So here's just kind of another thing. So if we choose one principal component in this case, that's explaining 50% of our model, and there's 50% left over in our residuals. We add our second component. It can explain up to 50%, but not more by definition of the math. In this case, we're getting another 25% of our information explained. So now our model is explaining 75% of the data, and there's 25% left over. Principal component 3 adds another 15%, so that our model is now explaining 90% with a 10% residual. Where you stop along this curve is solely dependent on the type of analysis you're doing. If I'm working in an analytical or pharmaceutical laboratory, I often need this to be over 85–90%. If I'm doing something instead looking at sensory analysis or surveys that people are turning in, I might be very happy with something as low as 30–40%, because if I can explain a third of the population, that's a valid information, just because people are so variable from each other. So in our scores plot, we want to again look at how well our data is distributed. We look for sample patterns, groupings, similarities. In this case, we've got different peas that were harvested at different timings. And in this analysis, we can see that it starts at an early harvest here, and it moves towards a late harvest. And this is described solely by tasting the peas. So there is this time gradient that you may see. When you're interpreting your loadings plots, you can see that if anything that is completely opposite from each other, the variables that are opposite from each other, are anti-correlated. That means that as the sweetness, fruity, and pea flavor values go up, then the hardness, mealiness, and off flavors are getting lower values. These variables here are correlated with each other. Anything that's very close together, that means that they are moving in the same direction at the same time in that particular component. All right, this is really handy for variable reduction. If you don't quite understand what pea flavor means, then perhaps that's something that you would remove from your analysis, because it correlates so closely with fruitness and sweetness, which most people can understand a little bit better. If you're doing analytical testing, if you have a cheaper, quicker test as opposed to a long, expensive, dangerous type of test, you may be able to replace it by seeing that they correlate so closely. I talked about this already, that once all of your variables are falling inside this 50% line, then it's very low importance in the model. Now I have an example of Octane, and this will come to touch on a question that I did get about if you're using infrared data, some spectral data, do you recommend scaling the data? Typically, no, because the variation between the variables is important information. It's not noise. In the case of when you're on very different scales, like temperature and pH and conductivity, you need to get those on the same scale. When you're looking at spectra, they're already on the same scale, and how they the amount of variation between those is important information. So let me open up my Octane example. So this is NIR spectra of different fuels, looking to determine how much octane is in them. But we're just going to do a PCA analysis first, just to kind of get a general overview, see if there's any information in there that is useful. Some of these also had an additive in them. Some of them have ethanol added to them. So we will take a look to see if that affects our analysis as well. So first thing I might do is do that descriptive statistics, just to kind of get a peek at it. And we can see that there are different areas that have more variation to them than others, especially up here. Okay, we can see there, because this maximum whisker is really tall, but you can see that the box part of the box plot is still pretty small. That's telling me that there may be some outliers. There's a few data that are very different than the others. Okay, so that's just something to keep in mind. Now what I'm going to do is analyze my principal components analysis. Make sure that I'm just using my spectra. And in this case, I have a training set and a test set split up. We don't need to weight anything. Our validation for this will still be full because we only have 26 in our samples. Press OK. Now the first thing we look at is how many components do we want to use. All right. In this case, I would say it's very clearly a 2 principal component problem. Okay, so we don't want to use any more than 2 principal components. If we take a look at our scores here, you can see we've got 2 data points that are very far away from the rest of the data. So that's fairly unusual. We want to take a look at that, see if there's something special about those particular data points. What I'm going to do here is I'm going to right-click my sample grouping, and I have some rows that talk about the type. Is it a low, medium, high? So we might look at that first to see if that's what's causing them to be different. And no, there's no real difference there. There's a medium and a high value there. If I put my legend on, you can see. And you can see that everything else is kind of lining up along principal component 2. This is a very clear indicator that there may be some outliers, which may be these 2 data points. Let's right click again, sample grouping. I'm going to clear all of these. And now I'm going to take a look at this additive. Now what we see is that these 2 data points are very clearly the additive. And that's what's making them very different. And that's separating across principal component 1. Now we can go and look at our loadings to see what's different about that spectra for the ones with the additive. And these are NIR. The loadings, when they're plotted as a line plot, you can interpret them just like you would a spectrum in general. So we can take a look. Everything's pretty low except for this area here around 1410. Now, if you know your vibrational spectrum, this is where your OH peaks are. And if you remember, the additive is ethanol. So it makes sense that ethanol is what's separating these out from everything else. So what we may want to do is go look at these without including those outliers. I'm going to go at the top here. I'm going to choose to mark 1 by 1. I'm going to choose those 2 data points, go to my analysis node, right-click, and say recalculate without marked samples. Say OK. Now we still have a 2 principal component analysis, but our scores make a lot more sense. They fall over the entire area. Our loadings are going to now be in our branching areas, our carbon-hydrogen, carbon-carbon bonds, and that makes a lot more sense. And if we right-click, we can do sample grouping. We can clear based on our low, medium, high. And we can see that in 2 principal components, there is a general trend. This is suggestive that we could go and make a PLS, a quantitative model, to determine the octane content based on this data. I have a question about the loading plot, either explaining 50% or between 50 and 100%. Is it more graded so variables close to the line separating inner and outer area but on each side? Aren't they also close to with respect to amount of explanation? I'm not exactly clear on what you're asking. If you could elaborate, that would be very handy. for me. I can show you the correlation loadings on this line plot as well. It looks a little bit different. So basically, it's anything that's between these two sets of lines at the top and at the bottom. Those are the areas that are showing the most variation in the spectra themselves. It's a little bit hard to interpret when you do the correlation loadings on spectral data. So I tend not to use that as much. I just interpret it as spectra directly. But this is one way that it can help you identify if you want to do some variable reduction. If I did not want to use my entire wavelength range, I could come in here and select, I know that these areas are important. Oops. These areas are important. Okay. And then I could recalculate with those marked variables, or actually what I'm going to do is with unmarked downweighted. So it multiplies everything else by a very tiny amount so that you still have placeholders so you can interpret your spectrum. And now only these particular wavelengths are included. And sometimes that can make your model a bit better, a bit more robust, so that it's not worrying about if there's any strange things that happen in these other areas. That is all I have for this example. Let me go back to here. So, in conclusion, how do we become a good data analyst? Okay, so the general workflow is you're going to collect your data, and then you check your data with, say, principal components analysis. Make a model, and then you check your model. Make sure that it makes sense. Interpret it. Apply the model to new samples, and then you check your results. Again, we only went over this kind of first area, so the check your data, the MVA calibration, and validation. Moving forward, you would do some applying the model to new samples. So here's some basic rules. You want to make sure to use representative calibration and validation data. Make sure you're evenly distributed, spanning all major variations that you are expecting. Select an appropriate validation method. Cross-validation is a good starting point. Certain regulatory entities require a test set, so we can talk about that in more depth later. Look for outliers, like I showed in the Octane. You decide whether you want to keep them or remove them. They can carry a lot of information, but they can damage the model, so it really depends on what you're looking at. Choose the number of principal components that you want to use, and you need to make sure to do that first before you start doing all your other analyses. Interpret your patterns in your data by studying the scores plot. Look to see if they're separate subgroups. If you're doing a classification, you may have to make models for individual subgroups. Interpret those variable relationships. Study the loadings plots. Once you're happy with the models that you have built, then you can go through and really analyze, interpret those loadings. We didn't talk about this, but be careful about transforming or pre-processing data unless you know what you're doing and why, because you can destroy your data. And then eventually you will check how well your model performs on new data. So you take new data that you know where it stands, put it into the model, make sure that it behaves the way you expect it to, so that then you can go and do your new, use it to replace your other methods. And then practice makes perfect, or I like to say practice makes better. I've been doing this for about 10 years now, and I'm learning new things every day, even in these basic courses and webinars. So it's a constant learning process, so don't forget that. All right, that is the end of the slides, and I have a few questions that I will answer here. And I'm just going to put up my email address, so in case there's anything that we weren't able to cover today, you have more questions, you're more than welcome to email me, and I will get back to you as soon as possible with that. So let me go back to my P's data, or my McDonald's data, apologies. So someone is asking how I identified that principal component 1 is energy and fat, and carbohydrates being principal component 2. So that's based solely on this correlations plot. All right. So what I'm looking at here is I'm just plotting the values of my loadings. Okay. So essentially the cosine. Things that are far from the center along the x-axis in either direction are going to be important variables that describe principal component 1. Anything that's near the center here, that's not far from the center, it basically is at a 90-degree angle from the direction of the principal component vector. Therefore, the cosine is 0, so it falls very close to the center. Things that are closer to being absolutely directly in line with that principal component would have a cosine of 1 or a -1, which would put them very directly on here. So we can see energy here has a value of 0.81, fat has a value of 0.91. So those are very important in principal component 1. Here, saturated fat, if you look at that second number there, 0.01, okay, that's for principal component 2. That doesn't affect principal component 2 at all. So principal component 2 vector does not go towards the direction of saturated fat at all, but it goes pretty closely with carbohydrates, which is 0.92 in this case. Nothing else has a very high, maybe protein, it's 0.6. That's right on the edge, really. If we track this over, if I make an arrow and I'm going to bring this back to that center line, if we compare how far that is away from this point, that's how it's telling me how important it is. I hope that answers your question. Okay. Explain the meaning of with or without, marked and unmarked. Okay, so let me open up my Octane data again for that. Okay, so in here I went and I marked. You see how there's little circles around those data points? And you'll notice it circles them in all of my other plots as well. That helps you go through and do some more analyses, get some more understanding about what's happening with those particular samples. And that's a little bit out of the scope of this webinar, but just keep that in mind. So once they're marked, we can either decide, okay, these marked ones, in this case, I'm considering them outliers. So I want to recalculate the same analysis, but not to include those. So when I recalculate, I'm saying without marked samples. So I don't want to include the samples that are marked. Okay. When I chose certain wavelength ranges in here, I can mark those. You see there's circles around the individual wavelengths that I care about. Same thing. I can go in here. I can either recalculate with those marked variables, which is fine if you're doing, like in the McDonald's example, if I wanted to remove the saturated fat one, I would just say without marked sample. In this particular case, though, because we're looking at a spectrum, and I'm going to show you, if I just do with marked variables, the loadings become harder to interpret because you can't tell what's missing here. Okay, we've broken the axis, but it's not obvious that it's broken. However, if I do the same analysis and have my unmarked, the ones I don't care about, down-weighted, then I still have placeholders that are just zeros for the areas that I didn't want to see. And so it's much easier to interpret the spectrum as if it was originally plotted. So that is all the questions I am seeing at the moment. Again, if you have any remaining questions that I haven't touched on, please just email me. Here's that email again, hbrook@kmo.com, and I'm happy to answer any more questions you have about this. So I hope everyone has a great day, and that this was helpful and useful for you.